Welcome to Press Podcast number 110, and today we're talking about how surface roughness affects airfoil performance. So we're going to be looking at wind turbine performance and how different surface roughnesses, which they artificially put onto these wind turbine surfaces, affect how they perform. And this is a topic that I've talked about quite a lot in other podcasts, how it's not only the Reynolds number or even the turbulence density level that affects the performance of airfoils and objects in general, but also the surface roughness. And one major reason is because this surface roughness significantly impacts where the transition point in the boundary layer occurs. So to look at this phenomenon and the effects of this resultant change in transition, we're going to look at a paper called Experimental Investigation of Surface Roughness Effects and Transition on Wind Turbine Performance. And this is open access, so you can find it in the link in the description. So let's begin. So wind turbine operation is frequently affected by a decreasing performance over time, and this is usually assumed to be caused by erosion, contamination, and roughness occurring on the rotor blade, especially at the leading edge. This phenomenon has not yet been thoroughly studied. Some qualitative tests on airfoils have been done, whereas the loss of airfoil performance has been measured, but the way to extrapolate the two-dimensional measurements to the three-dimensional airfoil behavior is not straightforward. So up until now, 2D measurements have been the standard, but three-dimensional behavior is also important because for not only airfoils that are swept, but also rotating blades as well, there is a significant three-dimensional effect. So the level of laminar flow over the wind turbine blades can be affected by their surface roughness and the turbulent inflow. So this is whether the flow has a very high turbulence density already and what the Reynolds number is. And these affect the aerodynamic performance. The chordwise position of the laminar to turbulent transition on an airfoil can be easily predicted through 2D computations, but it's not so accurate for obtaining this when it's a three-dimensional rotating blade. So the main objectives of this test were to measure the effects of a roughness simulation material installed on the airfoil leading edge of both the wind tunnel model and wind turbine blades. So they're going to be testing wind turbines in real life and then looking at wind tunnel models and grouping them together and seeing what they can find. And they want to analyze the effect of this surface roughness on the laminar to turbulent flow transitions with surface microphones as well as some other methods as well, which we'll cover. With the surface roughness, surface microphones detecting where the laminar to turbulent transition occurs is really cool, and it's I'll explain it briefly how it works. So if you have, let's say, a boundary, so you have just the wall, and then you have the flow going over it, and it starts out to be laminar, then it transitions to turbulent. There'll be a point where if you look at the amount of energy that the flow has across the different frequencies, it will change. So if you have on the x-axis the frequency, and on the y-axis you have the amount of power. So the you can either measure this in pascals or in decibels or whatever you want. You'll find that when it's laminar, it will be a fairly low power spectrum. So the power will be quite low. As soon as it transitions to turbulent, it will be significantly higher, but also there will be some more jagged peaks around. So this is quite indicative of a turbulent boundary layer because obviously turbulence is quite random, which means that there is a lot of unsteadiness at all different frequencies. So the power spectral density, so the amount of power that all these fluctuations have in a turbulent boundary layer should be significantly higher than a laminar boundary layer. So that's how they can use microphones, because microphones do detect the amount of power that something has at certain frequencies. That's how we measure sound. So that's one way that they're going to be testing where the transition point is, and this is really cool. And we'll discuss more how this works a bit later and their setup. So let's talk about the experimental approach. So both types of experiments, roughness simulations and transition position measurements, have been performed on a 2D airfoil at a wind tunnel and also on rotor blades at an operating wind turbine. The airfoil geometry used at this wind tunnel test is the same as one of the airfoil sections of the tested wind turbine blades and corresponds to the 18% relative thickness NACA 633-418 airfoil. This is important to note. The blade section with this geometry, so the NACA 633-418, is located in a tip region around 93% radius. This is very important to note because wind turbine blades do not have a constant profile along the entire span. It does change. This is for a couple of reasons. One, because as you go along the span, you get a greater rotational velocity, so a greater translational velocity, because the rotational velocity is the same, but you're further away from the point at which it rotates about, so you get a greater translational motion. But also, you don't want to produce as much lift near the wingtip for similar reasons as for an airplane, because you'll get greater losses there. So by changing the airfoil profile, you can increase the efficiency and the effectiveness of the wind turbine in total. So the airfoil profile that they have corresponds to almost, like it's quite close to the blade tip. It's 93% away from the axis of rotation from the blade. So this corresponds to a NACA 633-418 airfoil. So the roughness simulation has been attained by applying sandpaper to the leading edge of this airfoil. The sandpaper has a normalized size of its grain material designated by its grit number. So sandpaper is probably the most underrated tool that aerodynamicists can use for a few reasons. For example, here, they use sandpaper as effectively a boundary layer trip. So what boundary layer trips do is that they introduce a lot of turbulence at a certain location, which then hopefully will then propagate downstream and break down into three-dimensional turbulence and just make the boundary layer turbulent. So it's very effective using sandpaper for that aim. The second major benefit of sandpaper that aerodynamicists should really jump on is its ability to control the surface roughness. So when you look at any paper, almost never you'll have the researchers documenting how rough the surface was. And this is for a very good reason. The reason is because it's quite difficult to do. You need to have a surface roughness measurement tool, and they are quite uncommon. You can get them, but they are quite uncommon. But if you don't want to use a tool, you can always use sandpaper. So sandpaper has grit levels, and these grit levels are very strict in terms of like how rough they are. So if you get a grit of, let's say, P60 or P240 or P1000 or whatever, you know that that roughness on this surface is going to be a certain amount. So when you start sanding your object, as soon as the object is no longer getting sanded, so you sand for, let's say, half an hour and it gets smoother, then you sand for another 5 minutes and there's no more smoothness, like it's not getting smoother, then you can say that, okay, this roughness corresponds to this surface roughness, which is going to be given by the sandpaper. So now you can quantify what the surface roughness of your object is. So sandpaper is very useful, and we should use it as much as possible as an easy way to determine what our surface roughness is and control it. So this sandpaper that they're using on the leading edge to trip this boundary layer, they say this allows for an easier repeatability of the tests because sandpaper is so strictly controlled its roughness, and for the reproducibility by CFD. It is a cheap and very accessible material and can be easily installed with double-sided tape on the model or blade covering the desired area. One thing that I should note about this is with the double-sided tape and the sandpaper itself, they have their own thickness, and this could trip the boundary layer artificially. So if you want to trip the boundary layer based on the surface roughness, it may not be tripped from the surface roughness, but actually from the height that this additional layer takes up. That is another form of tripping the boundary layer. So you want to have that as thin as possible. So the boundary layer transition can be derived from the analysis of the power spectral density spectra of the high frequency surface pressure fluctuations. So as I mentioned earlier, when you look at how much energy these fluctuations have in the frequency range, then you can tell generally how much turbulence there is in the flow. The use of embedded surface microphones for the analysis of boundary layer transition has been performed by many years ago by DTU, a group, I guess, in the Dan Aero project. I'm not familiar with this, but I'm guessing it's some research group somewhere, and has allowed the implementation of it on wind turbines. But this group has the inconvenience that the microphones have been installed during this process has the inconvenience that these microphones must be installed during the manufacturing process, which makes sense. You have to drill like holes into the blade and stick them in and wire them through the blade inside. Recently, the use of very thin microphones can be installed over the blade surface. The work performed in this experimental project has been focused on the demonstration of the use of these very thin microphones. So that means you can position them ad hoc and or any way you want, really, and don't have to worry about the manufacturing process to get them in where you need them to. So that's very useful for researchers. So with their test sections, so the free stream turbulence level in this test section is 0.02%, which is really good. That's at a wind speed of 10 meters per second. When you go up to 80 meters per second, when the turbulence density level is 0.07%. So that's, again, still really good. Most wind tunnels, aerodynamic wind tunnels, are between about 0.1% and 1%. So this is like an order of magnitude better. So for this blade, for this airfoil section, for a free stream velocity of 80 meters per second, this corresponds to a Reynolds number of 3 million. So that's well into the turbulent range. So we expect somewhere along this airfoil, transition will occur. So we usually will expect transition to occur at about 200,000 Reynolds number, 500,000 Reynolds number, around that range. So being 3 million is well above that. So let's talk about the wind tunnel test description. So figure 3 shows a scheme of the model installed in the test section. So figure 3 shows like a cross section of the wind tunnel test section, and they have a wing airfoil going through the entire test section. So there is no wing tip. It goes from one wall to the other. So this is kind of two-dimensional. When there's completely attached flow, this is definitely two-dimensional. When you have separated flow, you could argue that there is some three-dimensionality to the separation, but arguably this is two-dimensional. So let's talk about the surface roughness test. So the aerodynamic coefficients of the airfoil have been measured at around number of 3 million for a clean airfoil and one with different surface roughnesses. The surface roughness distribution was simulated by applying sandpaper of 3 different grits, so P240, P80, and P240. And these cover the upper and lower surface of the leading edge, and with 3 different chord length extensions from 4%, 8%, and 15%. So what does this mean? So with sandpaper, a grit level of 240 is finer than P80. So the higher in number you go, the finer it becomes, the smoother it becomes. P40 is like pretty much the coarsest you can get, and it's very rough. P240 is quite smooth now, but there is still a little bit of surface roughness, and the grits can go up to like 2,000, 3,000, even higher. So they have these different surface roughnesses, and they're placing it on 4% of the chord, so from the leading edge, 4% downwards, 8% downwards, and 15% downwards towards the trailing edge. So it's really just the leading edge part. Also, 2 reference conditions of a tripped boundary layer have been measured using zigzag tape of different thicknesses, 0.25 millimeters and 0.6 millimeters, positioned in both pressure and suction sides at a distance of 8% from the chord of the leading edge. So this is called a boundary layer trip. And what a boundary layer trip is, they if you have a boundary layer like a wall, then you just have an object of some description with some thickness. So the flow comes over, and then it reaches this object, and it has to jump over, and now behind it you get all this turbulence, and that turbulence will hopefully then break down three-dimensionally. Some boundary layer trips work better than others. One that they found that works very well is called a zigzag tape. So it looks literally like a zigzag, and you place it from the wing root towards the wing tip, so span-wise. And the reason why this works is because on each like peak and trough, you get different vortices forming of different signs, and there's just a lot of broadband turbulence forming. So this is very good because you have different frequencies forming, and this gives you the greatest chance of tripping the boundary layer. Now, as for the height, the greater the height, the more effective it will be, like the thickness of from the surface. This tape is, the better it will trip the boundary layer. But once you go so high, then you'll start to get like a macroscopic effect where you just like literally be sticking into the free stream flow, and you'll just have a massive drag penalty. So these thicknesses are 0.25 millimeters and 0.6 millimeters, so they're probably still within the boundary layer. In addition, some additional tests at lower Reynolds numbers of 2 million and 1 million were also performed in the clean condition and for the P240 grit surface roughness, covering 8% of the chord. So now let's talk about the transition tests with surface microphones. In figure 4, for the transition position experiments, 6 microphones were used. These microphones are 2.5 millimeters thick with a diameter of 16.2 millimeters. So if you notice the thickness, this is 2.5 millimeters thick, whereas the zigzag tape, which is actually boundary layer tripping tape, was at most 0.6 millimeters. So it's like 4 times thicker, these microphones, than even the thickest boundary layer tape, the tripping tape, sorry. So that's quite thick. A way to get over this thickness is you have like this, you can see in this picture in figure 4. If you can't see it, you can always watch our YouTube video or download the paper, or the video on Spotify should be available. So to get over this thickness, you can use like this circular, like aluminium, like this silver tape or black tape they have here, and inside it's vacant, so you can actually put the microphone in there. Then the tape goes over the top, so then it seals it to the surface. So there's like a nice ramp leading up to it. So that edge of 2.5 millimeters is now softened to a ramp that gently goes up to 2.5 millimeters from the surface. That is helpful for reducing the impact that these surface microphones have on the flow as well. So they said they wear this fairing to avoid steps with a diameter of 40 millimeters, these circular tape bits. The microphone and fairings are placed on the model surface through a double-sided base and finally fixed with a top adhesive pad, which has a diameter of 50 millimeters. The coaxial cables coming from the microphones are routed to the trailing edge of the model. So this is also another major problem. You obviously need to get the electricity to these, or like the electricity in this case, to these microphones. And this is through a cable. So you now need to put it in a certain location to reduce its effects on the airfoil. Ideally, it's best if you put it in the chordwise direction, because that's the direction of the flow. If you put it in the spanwise direction, then this cable will act more like a boundary layer trip, because it's going against, like perpendicular to the flow. So this is good that they're putting in the chordwise direction. They say that finally all the cables are attached to the trailing edge with aluminium tape and routed out to the test section through the floor. So aluminium tape is quite good for aerodynamic purposes because it's very thin. Usually it's around 50 microns. So that's far thinner than most other tapes, which are like 200, 300 microns. The data was acquired at a sampling frequency of 50,000 hertz. So that's very high. That covers the entire audible spectrum and more. The microphones were positioned at 2 different configurations. In both of them, 3 microphones were placed in the pressure side and 3 on the suction side. The microphones were staggered in a spanwise direction to avoid upstream microphones altering the flow to the downstream microphones. What does this mean? It means that they had one microphone close to the trailing lid, close to the wing root, the next microphone a little bit further out, and the next microphone further out again, so that in the free stream direction, they're not going to interact with each other, and their effects on each other will be minimized. Measurements were taken at 3 different Reynolds numbers from 1 million to 3 million, and the angle of attack ranged from 8 degrees to 10 degrees. In the second configuration, 2 stall cases were measured at angles of attack of 15 degrees and 18 degrees with a Reynolds number of 2 million. Pictures with an infrared camera were taken at these same conditions to correlate data with the microphones with the actual boundary layer conditions. So this is something that I'm not too familiar with, actually. Using infrared cameras to measure where the boundary layer transition occurs. The only way that I can really think of how this would work is if there's some sort of difference in temperature between the free stream flow and the blade. This would then change the cooling rates, which you could then see on infrared cameras based on the temperatures that they become. So I'm not sure if this is how they do it. They don't go too much into it in this paper, so I'm not really sure if that's how they do it. If you know anything about it, let me know in the comments below. Otherwise, I assume that they're looking at different temperatures based on different heat transfer rates, and they're using the infrared cameras to look at that. I'm not too sure. Anyway, they're using infrared cameras to correlate their surface measurements with the microphones to see how they line up. So the wind turbine field test description. In addition to these wind tunnel tests, they're looking at a real-life wind turbine. The wind turbine tests were performed in 2 different campaigns. The first one was dedicated to surface microphones testing for the surface microphones, and the second one was to the roughness simulations. So they wanted to test out these microphones first, see if they work, and then after that, they looked at the surface roughness. The surface microphones tested for transition detection section. So the transition detection test with microphones took place during 1 week in mid-October 2017. This week was selected based on weather conditions and technicians' availability. The needed weather conditions had to involve not too high a wind and dry weather. So the wind had to be below 10 meters per second, probably because if you start going above that, you get interference from like wind shear that's making noise as well, which would then corrupt the microphone's readings, and you wouldn't be able to really tell where the turbulence is occurring and where it isn't occurring. So you need to have low wind speed. The rationale behind the selected positions of the microphones have been to ensure that on both sides, there are measurements both in the laminar part of the flow and in the turbulent part of the flow. So if you put all the microphones really close to the leading edge, potentially you'll just be in the laminar range the entire time. If you put some in the leading edge section, some in the trailing edge section, you at least will then capture the laminar flow and the turbulent flow so you can tell the difference. So that's what they're trying to determine here. They say that some were put very close to the leading edge as well as much further downstream. And this also has the impact that an exact position of the transition point cannot be derived from these measurements, which would require at least to mount 8 microphones on the same side. So in other words, by having only 3 microphones, one like close to the leading edge, one bit further downstream, and one further downstream again, there are zones in between these two microphones, each microphone, which you cannot measure because obviously there's no microphone there. So what you can say is that between these two microphones, transition did occur somewhere. So they want to have a higher resolution, they're saying, but they don't have that ability. However, they still got insight into the spectrum at different conditions of the boundary layers. So the positions of the microphones were quite different for the suction side and pressure side. For the suction side, they're closer to the leading edge, one at 5% from the leading edge, one at 10%, and one at 20%, and one at 40%. On the pressure side, however, the first microphone was 10% from the leading edge, then 20%, then 40%, then 80%. So why is that? The reason why is because as you increase angle of attack, the transition point on a boundary layer will actually creep towards the leading edge. So on the suction surface, the boundary layer transition point will be closer to the leading edge than on the pressure surface. Hence why they put the microphones further downstream for the pressure side and further upstream for the suction side. So let's talk about the roughness simulation test. For the roughness simulation, the 3 blades were covered with sandpaper in the leading edge area in the same way as the wind tunnel model. The objective is to obtain power data of the wind turbine with the simulated roughness installed and compare them to the power obtained at the clean conditions so that the roughness effects can be evaluated in terms of power loss. Also, these results can be cross-checked with the data obtained from this 2D airfoil in the wind tunnel tests. Remember how the airfoil in the wind tunnels span the entire test section, so that's effectively 2-dimensional, whereas in the wind turbine in real life, that's 3-dimensional. So they want to see how these two differ, or if they differ at all. So in order to stand up to the outdoor climate conditions, the selected roughness simulations material was a R205 aluminium zirconia sanding belt. Long belts of 200 mil by 750 mil were used to build the roughness strips, and double-sided 3M tape were used to install them on the blade. As a side note, 3M tape is amazingly good. I see it everywhere. So the roughness simulation material was installed on the 3 blades covering 5 meters of the span, so between 32 meters from the root and 37 meters from the root. And the chord-wise extension was 15% in this case. So in the wind tunnel test, they looked at many different coverage areas. In this one, they only looked at 15%. And the grit was P60, which is equivalent to a mid-grain size of 269 microns. So this is what I mean here, where sandpaper is so well regulated that they can tell how rough it is just by a single number. So P60 means that the average grain size is 269, and there's obviously some span of that, so some will be a bit lower, some a bit higher, but on average it's about that. And it's great because you can just go to any hardware and get the same sandpaper grit, and you know that you're going to get that roughness. So to decide the grit size to be used in the field tests, on what grit size should be used, the main consideration was to use an equivalent size used in the wind tunnel in order to correlate the data. The wind tunnel tests were performed at a Reynolds number of 3 million with an airfoil chord of 0.6 meters. However, on the blade, these parameters are not fixed, since in the selected blade, the chord varies from 1 meter to 1.5 meters. That Reynolds number is also not a fixed value because it changes with the wind conditions and also with the chord dimensions. So on a wind turbine, the further you go out from the blade root, the faster the translational speed is. So that's going to change the Reynolds number. Also, it's not only that, but the blade actually gets thinner. It's a bit tapered, so that will also affect the Reynolds number. In table 2, they have the range of Reynolds numbers that the blade will see between 32 meters from the blade root and 37 meters from the blade root, and different wind speeds. This ranges from 3.3 million to 6 million. So that's going to change the boundary layer profiles and where the transition will occur. So making the equivalent grain size for the different wind conditions of the blade showed that it would correspond to values ranging in most cases between P40 and P60 grit sandpapers. Therefore, they decided on P60 would be the best. So let's look at the preliminary results from the test, from the outdoor test with the wind turbine. So what are the effects of the surface roughness on the aerodynamic performance of these blades? Figure 7 compares the clean surface case with different cases of the P40 grit roughness chordwise extension, whereas Figure 8 shows plots comparing the aerodynamic coefficients for different grain sizes. So for Figure 7, we can see that pretty much anytime you have surface roughness, the performance of the blade drops. So when the airfoil is clean, the maximum lift coefficient is like 1.2, 1.25. As soon as you put on any roughness, then it goes down to 1, so it drops by like 20%. And this also, it isn't really affected by how much of the leading edge is covered with this sandpaper. They have 4%, 8%, and 15% coverage, and the maximum lift coefficient is the same for all of them. It dropped by 20%. However, the stall pattern for the 4% coverage is better than any of the others. So that means that surface roughness really just makes these airfoils perform much poorer at higher angles of attack, which I'm a little surprised at, because typically in the stall regime, having tripped the boundary layer sooner would usually help the flow state attach better. However, it really depends on how much higher momentum fluid from the free stream velocity is from the free stream flow would be entrained as well, which in this case, I guess not much, because it doesn't really benefit the stall pattern very much. So surface roughness is bad for the maximum lift coefficient and the stall pattern. Also, the maximum lift to drag ratios plummet dramatically. At 5 degrees, the clean airfoil has a lift to drag ratio of 120, which is phenomenal. As soon as you put on any surface roughness, it drops to 40. So like a 66% drop. It's terrible. This was for quite a rough sandpaper, 425 microns. So that's probably for the P40 or P60 grit. Now let's look at the effects of the different grain sizes on the airfoil performance when it's just located on 8% of the blade. So from the leading edge to 8% down of the chord. Now, for the different surface roughnesses, we find that as you increase the surface roughness, the blade performs worse. So again, the maximum lift and stall conditions are not really affected too much, but the lift to drag ratio is dramatically reduced. So when you have a P240 grit, so that's very fine, the maximum lift to drag ratio is 51 about. As you go to P80 and P40, it drops to 44 and 42. So there's a 20% drop off there, just with a slight increase in surface roughness. So that we can categorically say here that surface roughness is not good for these blades. And I guess you could extend that to a lot of airfoils, saying that these surface roughnesses generally would not be very good. However, as I mentioned, some boundary layer tripping is actually very good for keeping flow attached at higher angles of attack, so it could benefit stall. Just in this case, for some reason, they didn't find that. It might be for this particular airfoil. Now, in addition to that, Figure 9 shows the trends of the minimum drag and maximum lift to drag ratios for different configurations tested in the wind tunnel. So we were looking at the wind turbine blades. Now let's look at the wind tunnel data. As it can be seen from the plots, the effects are almost linear with the extension of the roughness, but not with grain size. So in other words, as you increase the amount of the blade that has this surface roughness, the effects that it has on the drag are linear, and the lift to drag ratio also linear. So that is, as you increase the amount of blade that has this surface roughness, the drag continually increases linearly. So when you have only 4% of the chord covered, the drag was 110 counts, so 0.11. As you increase it to 15%, it jumps to 120 or 0.12. So that's about a 10% increase. And this increase is about the same across different grit sizes as well. For the maximum drag ratio, as we mentioned earlier, we found for 8% that we get a massive reduction for any surface roughness, and the greater the surface roughness, the worse the lift drag ratio becomes, and that is also the case for different angles of attack as well for the two-dimensional airfoil. The two-dimensional airfoil shows that for very fine sandpaper, so P240, for 4 degrees, the maximum lift to drag ratio is 54. As you go to 15% of the airfoil is covered, the maximum lift to drag ratio drops by about almost 20%, or maybe 10%, 15%. So we can conclude here that, again, for a two-dimensional case, the rougher the surface is, the worse the performance of the airfoil becomes, and also the more of the surface is covered, the worse the airfoil performs as well. So let's move on to the results from the transition measurements with surface microphones. So now we want to see how these microphones can tell where the transition point occurs. So figure 10 shows the power spectral density of the surface pressure measurements from the microphones. The data from the wind tunnel can be cross-checked with an infrared camera that shows the areas where the flow is laminar and turbulent on the model. So in figure 10, the infrared picture, it shows two different regions, like two different grays. The gray closer to the leading edge is much darker than trailing edge. So I'm guessing this somehow reflects the heat transfer or heat temperature of this airfoil somehow. So that's the infrared section. I'm not going to cover that because they didn't really discuss how they did this properly, and I don't understand it myself thoroughly enough. But for the microphones, it's quite clear. So there are 3 microphones, one at 10% of the distance from the leading edge, one at 40%, and one at 80%. And they have the frequency spectrum from 100 hertz up to 10,000 hertz. And for the 2 microphones closer to the leading edge, so 10% and 40%, the power spectral densities are very similar. However, as we get to higher frequencies, there is a lot more power in this region when we go further downstream. So 40%, there is a lot more power here, which indicates that there is now some flow there's some turbulence that's showing some energy in the higher frequency range. As we go to 80%, we now see not only a massive increase in the amount of power the entire spectrum has, it increases by like 6 decibels across the board, which is 4 times as much power as the other 2 regions. But we also get peaks at lower frequencies. So what this means is we're probably in a turbulent zone now because we have more energy at these higher, at all frequencies, which means that there's more turbulence. But also we have a lot of energy at low frequencies. So that's now small, like low frequency scales have a lot more turbulence, and that means that we have a turbulent boundary layer here, and it's very easy to see between these cases. So they're quite easy to recognize where turbulence is occurring from these surface measurements with these microphones. They say here that some of the peaks indicate Tolman slitting waves, and that leads to instability. So let me discuss quickly what Tolman slitting waves are. So if you have a surface and you have the flow going over it, and you get a boundary layer forming, obviously, you then have these like little waves forming, and these are called Tolman slitting waves, and these are arguably the best known or most commonly known boundary layer transition mechanism. So what these waves do is, as you go downstream, if the Reynolds number is high enough, they'll start to grow and they'll start to break down 3-dimensionally, and this will create just general turbulence, and this will then result in a turbulent boundary layer. If the boundary layer is if the Reynolds number is too low, these Tolman slitting waves will actually start to die out, so then you won't get turbulence forming. So that's what they're mentioning here. They can see that there is TS waves forming here. So moving on to figure 11. Figure 11 shows the spectrum of the suction side and the pressure side when the microphones are installed on the blade in an operational condition. So in other words, now we're looking at 3-dimensional at the outdoor wind turbine results. So 3-dimensional results. They say on the pressure side plot, the spectrum for the 40% and 80% positions are quite similar and rather flat, indicating a boundary layer, a turbulent boundary layer. And when the microphone is at 20% and 10%, the positions, these correspond to a laminar boundary layer. For the suction side, the plot shows turbulent spectra for 40% and 20%, whereas at 10% and 5%, it is difficult to make a clear characterization. So let's break this down and discuss what's going on. So for the suction side, when I mentioned that the microphones were closer to the leading edge because transition occurs closer to the leading edge, this is validating that. So they've got 4 microphones, one at 5%, 10%, then 20%, then 40%. And for the 5% and 10% zones, there is a lot of energy, like there's a lot of low energy. So the frequency spectrum is lower in energy than at the other two locations. This indicates a laminar boundary layer. For the 20% and 40%, the locations, the energy spectra is much higher across the board. So this indicates a turbulent boundary layer because there's now just general unsteadiness with a lot more energy, which is turbulence. For the pressure side, the turbulent transition doesn't really occur until between 20% and 40% from the leading edge, somewhere in there. Then we get the exact same kind of thing happening where downstream, the boundary layer has a lot more turbulent energy across the board, whereas upstream from that location, the boundary layer has a lot less energy, indicating a laminar boundary layer. So these microphones are very good at detecting at how much energy the flow has, and in which frequencies, so that indicates where this transition occurs. So in conclusion, the effect of different chord-wise extensions and grid sizes on roughness on airfoil performance has been evaluated with a wind tunnel test and with an actual wind turbine out in real life. Chord-wise roughness extensions increase between 4% and 15%, and they have shown to produce a close to linear degradation in effect on the airfoil minimum drag and maximum lift drag ratio. So in other words, the more roughness you have, not only in the amount that the roughness covers of the airfoil, but also how rough this surface is, the worse the drag becomes and the worse the drag ratio becomes. And also the worse the lift also becomes at the maximum point. So that's in this paper. And if you like to, make sure to like, subscribe. And if you want to get better at theory yourself, so we're going through theory here, for example, you can take one of our courses in the link in the description. And if you want to get better at CFD, you can take a course as well in the link in the description. And if you want to make your experimental results 2 to 4% more accurate, check out that Atmosphere Hawk, because that's an instrument we make which accurately measures the density of air. And the reason why this is important is because the density of air changes by about 2 to 4% every day, and it changes more between days, weeks, months, seasons. It can change up to like 15% quite easily. On our site, actually, we have some graphs showing how it does change, like from regular data from real life between days and weeks. And it's very alarming. So you need to make sure you measure the density of air, and Atmosphere Hawk does that very accurately for you. And also it makes your CFD validation data more accurate, because this data now, the density that you've measured the air at is actually the same as your CFD that you're simulating at. So you can trust your CFD validation data and your CFD simulation much more now. So that's the link in the description there. And I'll see you in the next podcast. Peace out, amigos.